Hello. I'm sorry I didn't buy chocolate, but I think the remaining people are actually intrinsically motivated to participate and so on, so I think it's less of a problem than in other classes. So keep it up. Thank you. Right, where are we? We talked about the hyperbolic plane. We talked about discrete subgroups of PSL2R and how they act as Möbius transformations on the hyperbolic plane, and that we can use discrete subgroups to fold up the space. And if the quotient has finite volume, we call the discrete subgroup a lattice, and we saw an example that PSL2Z is an example of such a discrete subgroup of PSL2R, which makes the space kind of finite. Not compact, but finite at least. And I promise that this is sort of the starting point for getting a measure-theoretic dynamical system. And this is where we want to keep going. So proposition, let G be there's a list of properties, a nice topological group. Let gamma in G be a lattice. We'll talk a little bit about H measures afterwards, then I give you my standard assumptions on the group. So I have a nice group like PSL2R, and I have a discrete subgroup like PSL2Z, and I'm assuming that this is a lattice. Then the left H measure is also right invariant. This is called G is unimodular, if you hear the name, the phrase. You have heard it from me too. What this means. Moreover, there exists a finite, which comes from the lattice assumption, G invariant measure on the quotient G mod gamma, which is also G-ergodic. Yeah, and for making this work, we need a little bit more background on H measure, and let's just talk about it briefly, even though it's probably also in another course that you might or might not take. Okay, so an aside on H measures. We assume G is sigma compact, locally compact, metrizable. Topological group, let me also throw in this phrase and explain in words what I mean by topological group. Sigma compact, you know, right? It's just G should be a countable union of compact subsets. Locally compact, you know, it means every point should have a compact neighborhood. Metrizable, you know, there should be a metric on G that gives rise to the topology that we are talking about. Could also say metric, just I don't care so much about the metric, that's why not say metric and say instead metrizable. And topological means that the group is a topological group, which means that all the group operations, and there are anyway just two of them, should be continuous operations on the group. So taking the inverse is a continuous operation, and taking the product from the G cross G to G is a continuous operation. It's a continuous map. That's what topological group means. And we're talking about one topology satisfying all of these things together, of course. A measure, and I'm not writing it because we already mentioned this a few times. If you already have a nice space, and I say a measure, I mean a Borel measure. Don't go and look for some fancy sigma algebra that nobody's interested in. Just use the Borel sigma algebra. A measure M, or M index G, if I want to emphasize the group, is a left H measure if on G, if it satisfies the left invariance. So if I take a Borel set and I shift the Borel set by a left multiplication by some element G, then the measure of the set shouldn't change. Of course, the B is measurable. I want a bit more connection to the topology, because if I just say that, I could take the counting measure. Counting measure is defined in the Borel sigma algebra, but it's probably not the right thing, because what we're kind of interested in is a generalization of the Lebesgue measure, right? Lebesgue measure satisfies this as well, and is not the counting measure. If the group G is discrete, then I have nothing against the counting measure, because then the counting measure will be the right thing. But if the G is not discrete, then it's probably not the counting measure. Because I want that compact sets should have finite H measure. And I want that it's kind of far away from the trivial measure, from just mapping everything to zero. An open set should have positive measure if the open set is non-empty, for a non-empty open O in G. So there's a theorem that says the left H measure always exists under these assumptions. You could weaken the assumptions. Always exists and is unique up to scalar multiplication. I'm not showing the existence. I will tell you about the uniqueness. The existence we have seen in PSL2A very concretely by connecting it with hyperbolic geometry. And we define sort of a measure by coordinates. Three-dimensional group, we just have to do three integrations. And yeah, so for PSL2A we understand it. And I'm claiming that for many other groups you can give very concrete formulas that show the existence without you knowing the abstract existence theorem. But just to give you a hint, what you're trying to do in the proof of the existence theorem is you're trying to take a compact set, and maybe you take a very small neighborhood of the identity, and then you try to cover the compact set most efficiently by left translates of small neighborhoods of the identity. And you check how few elements you need. Because it's a compact set, you only need finitely many, right? And that gives you a left invariant notion, because if you now translate your compact set on the left, you can translate your best cover as well, and you get the same cover number of this compact subset. The problem is, of course, that it's not quite additive. If you have two compact sets and they get too close together to each other, then having a cover on the left part might help you to cover part of the other compact set, and then you might need one or a few less elements to cover the stuff on the right. So that's why you need a small subset, so that when you have two disjoint sets, if you have a small neighborhood of the identity, eventually they will not help you anymore. The cover on the left will not help you to cover on the right because they have positive distance from each other if they're compact and disjoint. But that, of course, means we need to take some kind of limit, and if we take the limit of the covering number, we just get infinity for everything, and that's not useful. So we need to normalize things. You need to declare a particular set and say, this set should have measure 1. And then divide the covering number always by the covering number of this compact subset. And then take the limit. And then you need to apply Tychenov and work a bit and prove all the properties, including that you get a measure, but it will work out. So that's the idea, that is sort of try shifting small neighborhoods and try to optimize what's the best cover you can possibly get. Okay, so that is all I want to say about existence, but I want to tell you a bit more about the uniqueness because it does play a bit of a role and it would be too big a gap, so I decided to include that in the discussion. Okay, so I'm working assuming that I already have a H measure, right? Because I'm not interested in the existence anymore. I'm assuming I have a H measure and try to say more and more useful things about this H measure. Lemma. Positive overlaps. Same assumptions. We have a nice group that's defined in the middle column here. And we have a H measure M. Let B1, B2 be measurable with both sets having positive measure. Then they exist G and G. There actually exist many, but I only care about one, with the measure of the intersection where I translate one of the sets. Let's say I translate B1, G B1, intersection B2. This intersection has positive measure. Right? If I have two non-empty sets, of course I can translate one of the sets to non-trivial intersect the other. And this is sort of a measure-theoretic version. I have a stronger assumption, but I want also a stronger conclusion. I have two sets of positive measure, and I'm able to create an overlap that is positive with respect to the H measure. Proof? I have a nice group, so I can use Fubini. There's no issue. So I'll use Fubini. I take this thing and want to describe this expression a little bit differently. So in particular, I just write it as an integral. Characteristic function GB1, H, characteristic function B2, H, dm, H. I can do that, right? That's clearly the same thing. And now I rewrite this characteristic function a bit. And this characteristic function is 1 if H is in G times B1. Right? That's by definition what's going on here on the upstairs. So H needs to be in G times B1. So there must be an element in B1 so that H is G times this element B. which means G is equal to H times B inverse, which means that this characteristic function is 1. Right? Where B1 inverse is just the image of the set under the inverse map. Okay? So I can put, instead of that, I can put this characteristic function, and now I just apply Fubini. Using Fubini, we get integral m gb1 intersection b2 integrated over g, over the whole group, with respect to our H measure, is equal to, and on the right I have an iterated integral. I can integrate in any order I want, and I integrate over h first. So I get characteristic function of b2h, integral, characteristic function, and I use the second expression, hb1 inverse g dmg dmh. Right, I had first I had the integrals in the other order, but I use Fubini and write it in this order. And here I see actually the H measure of HB1 inverse, except that I don't care about the H here because it's the left H measure. So I just see the measure of B1 inverse. So it's a constant, it doesn't depend on H. So when I integrate it multiplied by this, I can now finally integrate everything. I get the measure of B1 inverse, measure of B2. And now I'm claiming that I'm done with my lemma. Because if B2 is all of the group, then this here is all of the group, so I don't need to write the intersection. And I don't need to write the G anymore on the left here, because I just get the measure of B1. And I'm integrating the measure of B1 over the whole group. So I get the measure of B1 times the measure of the group, if B2 is everything. But we are doing more measure theory, right? So if this were 0, then 0 times infinity would be 0, but on the left I have plus infinity or something positive. In the case of B2 is everything. So what I'm concluding in the case of B2 is everything is that the measure of B1 inverse needs to be positive. I'm writing it down. If B2 is equal to G, we obtain the measure of B1 inverse must be positive. So in general, we see that the right-hand side here, measure of B1 inverse, measure of B2 is positive, and if this function of G would be 0 all the time, then the integral can't be positive. So this function of G must be positive sometimes, actually on a set of positive measure, and hence I've proven my lemma. Good? Any questions? Okay. Next lemma I call ergodicity of sorts. We have our group, we have our H measure. The left action of G on G is ergodic in the sense that if B in G satisfies that the translated set and the original set are almost the same for all G in G, then there are only two silly possibilities why this could possibly be true. One is the measure of the set is 0. If you translate the null set, it stays a null set. Sorry, there's a stupid typo. Thank you for looking puzzled. The measure of the set is equal to 0, or the measure of the complement is equal to 0. And then this will also be true all the time. Or you can also write it, think of it slightly more in terms of functions. If f from G to R is measurable, and for any G in G, f and H in G is mapped to FGH. Agree M almost everywhere. Then F is constant M almost everywhere. Again, if you throw away the null sets, all of these statements are kind of obvious. But with the null sets, they kind of require a little bit of input from measure theory, and the little bit input is the positive overlap from up there. But if a set doesn't move at all, then it needs to be the empty set or it needs to be everything. And here, this at all is replaced by this weaker assumption that the measure doesn't see that the set has changed. And then the conclusion is that the set is measure 0 or the complement is measure 0. Same with functions. Yeah, proof. For the first version, set B1 equals B and B2 equals the complement of B. I think G without B. If both have positive measure, we can apply the lemma. If M of B1, M of B2 is positive, we can apply the lemma above and find G and G with measure of G times B intersected G without B is positive. But this contradicts this assumption here, right? Here we said G of B is actually equal to B mod the measure, and here G of B intersects the complement on a set of positive measure. Contradicting. Our assumption. So that means the first version here follows really quite directly from the lemma above. Yeah, now I can. I kill the statement here, but we remember it, right? We remember it for a little while longer, that we can always create positive overlaps. For the second version, let I1, I2 in R be two disjoint intervals. And define Bj F inverse of Ij for j equals 1 and 2. If, again, the measure of both sets are positive, we can apply the lemma and obtain a contradiction. If you look at the composed function fg times h, then of course you sort of transport the values that f has in B1 to G inverse B1, right? Whatever values f has on the set B1, when you look at this translated function, the values you used to have on B1, you'll then have on G inverse B1. And if this translated set, G inverse B1, will then intersect B2, where you have different values on a set of positive measure, then you get a contradiction to the original function and the translated function being the same almost everywhere. So that means for any two intervals that are disjoint, the pre-image sets needs to have one of them must be a null set. At least one of them must be a null set. So you just chop the reals into countable many intervals, first say of length 1. Then only one of them can have positive measure, everything else will be, every other value will be only on a null set. And this interval of length 1 you chop into 15 sets, 15 million sets, it doesn't matter. You keep going, and every time you just have one interval that is important, and if the interval shrinks, you only need countably many intervals to find out what's the almost sure value. So you're using that. In the reals, you have countable separation, kind of. Using countably many intervals. In R, the lemma follows. A little bit of a measure theory exercise. Lemma. We are still working under the same assumptions. The left Haar measure is unique up to scalar. Proof. Suppose M1, M2 are two left H measures. Then I can do this trick that is sometimes quite useful. Just take the sum, that's another H measure. Why is it useful? Because the old ones are now absolutely continuous with respect to the new one. So that M1, M2 are absolutely continuous with respect to M. What does absolutely continuous mean? It means that if you have a set that is a null set for M, it must also be a null set for M1 and M2, which is obvious because M is the sum of these two. None of them are, they're both non-negative, so if M1 of the null set would be positive, then M of the null set would also be positive. And then it wouldn't be a null set. Which means we can find the Radon-Nikodym derivatives of M1 and M2 with respect to M. Let F1 be the Radon-Nikodym derivative, dm1 over dm, be the Radon-Nikodym derivative. So you have two H measures, and you have a Radon-Nikodym derivative for the two H measures. The Radon-Nikodym derivative is unique up to null sets, right? That's something we understand. I claim that this F1 is invariant in the sense of the second lemma. And if we understand that, then it must be a constant. And if F1 is a constant, then F2 is also a constant. And if F1 and F2 are constants, then M is a multiple of M1, M is a multiple of M2, but then M1 and M2 are also multiples of each other. Claim F1 is G invariant in the sense that F1 and, well, let me write it more slowly. H is mapped to F1 of H. H is mapped to F1 GH. Agree. M almost surely. And how can it not be? Because the H measures are left invariant, both of them. And the Radon-Nikodym derivative is unique. So I would be surprised by the opposite. This invariance is not surprising. But okay, let's think about why it's true. Now I'm erasing the thing, the goal, that's okay. Note that the claim implies by the previous lemma that M1, M, M2 are all multiples of each other. Right, there's a difference between absolutely continuous, having a Radon-Nikodym derivative, and being a multiple of each other, because being a multiple of each other means precisely that the Radon-Nikodym derivative is a constant. Not all functions are constants, right? So there's a difference. Okay, proof of claim. Let B be in G measurable G in G fix given, then I'm integrating my over this translated function. So I'm integrating f1 g h, but I'm integrating over the set b with respect to the measure m and the variable h, right? But m is a H measure, so I can do a substitution. I can make this, yeah, let me write this 1b h f1 gh dmh, and now I do a substitution and call this h tilde. And I'm multiplying my variable on the left, and the H measure is precisely made so that I can do this without any cost. There's no Radon-Nikodym derivative, there's no Jacobian or anything. So I can replace my h by h tilde, but of course here I need to make it look more complicated. I need to write G inverse GH, because then it will become characteristic function of G inverse B H tilde F1 of H tilde H measure H tilde, H measure M H tilde. So this was just bringing in the characteristic function. This was using the substitution, so I used M is H for this substitution. Now I use that F1 is the Radon-Nikodym derivative, right? So I'm having here an integral of F1, which is the Radon-Nikodym derivative with respect to the measure M. Forget the tilde now, right? You don't need to do this. So I can rewrite this as this is actually the integral. Yeah, this is the M1 measure of G inverse B, right? Which is the M1 measure of B, because M1 is H. Here I used dm1 over dm as the definition of F1. And now I do one more thing. I rewrite this again using the Radon-Nikodym derivative, so I can rewrite this as the integral over B of F1 H dm H. Okay, now we look at the beginning, at the end. Ignore the rest. Look at this, look at that. That this is equal to that is the defining property of the Radon-Nikodym derivative. That's the defining property, but this function satisfies the same thing. This is also the defining property of the Radon-Nikodym derivative. So this thing must be equal to our Radon-Nikodym derivative almost everywhere. That's the only thing we can talk about in the Radon-Nikodym derivative sense. As this is the characterizing property of dm1 dm, we see that h goes to f1 gh and h goes to f1h are m almost surely the same, identical. Yeah, and now the previous lemma, which was called ergodicity, kicks in, and we know that this function must be constant. But if this function is constant and m1 and m are multiples of each other, and then m2, same argument, is also a multiple of m, and hence we are done. The Haar measure is unique up to a scalar. There's a cool thing that you can do with a Haar measure now. If you have a Haar measure, you can push it by an automorphism. You get another Haar measure. Well, it can't be very different from the old Haar measure. So you actually get a scalar that depends on the automorphism. If you think about the Lebesgue measure of the n-dimensional vector space, the automorphism is a GLN map, right? The scalar will be related to the determinant of the matrix, right? But there's another thing you can always do. You can always apply inner automorphisms. Conjugation. And conjugation is related to multiplying on the left with something and multiplying on the right with something. But it's not clear what the left with something doesn't change the Haar measure, but the right with something may change the Haar measure. So let's just focus on this part, multiplying on the right. Given G in G, we can define M index G of B as M of BG, and easily prove that MG is a left Haar measure. Hence, there exists a delta of G, which is a positive real number, so that M of BG is delta G, M of B for all measurable B in G. This is called the modular character, this delta. You can actually show that it's a homomorphism. You can show that it's a continuous homomorphism. Never mind, we don't do that. Because in our case that we're interested in, this delta will be 1. And that's called the trivial homomorphism, right? That's continuous. No questions asked. If you just map everything to 1, that's okay. It's a homomorphism and it's continuous as well. But yeah. You agree? Multiplying on the right commutes with multiplying on the left. That's the greatest thing, and that's the only thing you need to show that this thing is again invariant under translation on the left, which is associativity again. We mentioned that last week as well. Okay, the group is called unimodular, and said this already, if this guy is always equal to 1, if the left Haar measure is also a right Haar measure. Okay, so that was the aside to Haar measures. Now we go back to our goal, and we think of this lattice inside G and want to understand how we can use this lattice to prove that G is unimodular, and how to use this lattice to create a measure on the quotient G mod gamma. But that won't be hard. But I guess we'll do this after the break. There's no point in me doing that now. Is there any quick question about the aside stuff concerning Haar measures? Good, then let's take the break. Okay, so we are back and online. This is the proposition that we want to prove, and we made some excursions into discussions for Haar measures, and now we come back to that proof. I start with a claim. Let B1 and B2 be two sets in G, measurable of course, with, and I write down a funny formula, but I'll explain it why this is relevant for us. So I take gamma and gamma, and I translate the first set under gamma in gamma on the left, where the lattice is. And I do the same thing with gamma and gamma and the set B2. And I insist that both unions on the right and on the left are disjoint, and that they give the same set in G. So B1 and B2 could be disjoint, but when I take their disjoint unions by gamma translates, then the two sets become the same thing. If this is happening, then the measure of the two sets are the same. Then measure of B1 is equal to measure of B2. Before we prove it, let's just agree on why it's potentially an important thing. Take a subset of the quotient of G mod gamma and take your fundamental domain. And now take all the points in the fundamental domain so that their coset belongs to the Borel subset in X. Then you get a set B1 that will have disjoint images because the disjoint translates, because the fundamental domain has disjoint translates. And the B1 is a subset of it. Yeah, we'll do this carefully later on. Proof of claim. Yeah, for the proof of the claim, we write B1 is actually equal to B1 intersection with this disjoint union on the right. Because B1 is a subset of the union on the left, right? Gamma contains the identity. So if B1 is a subset here and I intersect the left-hand side with B1, I just get B1, and when I intersect it with the right-hand side, I get this thing. Gamma B2, gamma in gamma, which I can rewrite, well, yeah, intersections and unions, they behave very nicely. I can write it as gamma in gamma, B1, intersection, gamma B2. Yeah, I haven't yet told you, but I'm really thinking, when I do this kind of thing, I'm thinking of lots of squares in the two-plane, right? I mean, that's my fundamental domain. I have a subset. B1 is a subset of this. That's my B1, and then I'm translating that. And the other set is maybe using a slightly different grid, translated grid. This is the kind of picture I have in my head, but I don't need that formally. Formally, I do everything here correctly, step by step. Okay? Now I take the measure. Measure of a disjoint union is a sum, right? Do you have a question? Because B1 is contained in this set here. And if I intersect B1 with a superset of B1, I get B1. And this superset is equal to that superset. So that's just, yeah, that. Good. Now I take the measure and calculate. Measure of B1 is equal to the sum over all gamma in gamma of the measure of B1 intersection with gamma B2. Right? And now I can translate this set by whatever I want in G on the left, and it would stay the same measure. So that allows me to move this gamma over here and make it a gamma inverse. Right? So I insert here, attached to the whole union, I insert here a gamma inverse and obtain is equal to sum over gamma in gamma, measure of gamma inverse B1 intersected B2. But inverse or not inverse, who cares? The gamma appears only once, and gamma is a group, so I don't need to write this gamma inverse here. I'm summing over all elements of my lattice and of my subgroup. But then this again looks like the measure of a disjoint union, because I have a sum. But which disjoint union does it look like? It looks like the disjoint union where B2 is the same and B1 is translated. So the roles of B1 and 2 are exchanged. So this is the measure of the disjoint union of the gamma B1 intersected with B2. But that is the measure of B2 by the same argument as before. Et voila. So we have the claim. But if you have the claim, then any two fundamental domains have the same measure. Because for a fundamental domain, the disjoint union is always G, and it's a disjoint union because it's a fundamental domain. This implies for two fundamental domains, F1, F2, that M of F1 is M of F2. Okay, we know that there is a fundamental domain. Let F in G be a fundamental domain. That is our assumption. There is a fundamental domain with finite H measure. That is really the assumption. Let G be in G. Then Fg, I translate F on the right, is another fundamental domain. Because when you take this, let's argue about it. So if I take the fundamental domain and do this disjoint union of gamma on the left, that is all of G, right? That's the characterizing property, the defining property of a fundamental domain. That is all disjoint, and I get everything. And if I now multiply both sides on the right by G, I get this. But that's the characterizing property of Fg being a fundamental domain. But any two fundamental domains have the same H measure. That's what is just said here. It's a special case of the claim. So F and Fg have the same H measure. But multiplying on the right, I said, introduces this modular character, except that we don't see it. So the modular character is 1. So the group is unimodular. Okay. Therefore, M of Fg equals M of F. This is equal to M of F times delta G, which implies, and so delta G is 1, i.e. G is unimodular. I need that the Hammersmith of the fundamental domain is finite, because then I can cancel it from the formula here, right? If my fundamental domain is a fundamental domain and the Hammersmith is infinite, I have nothing. So I'm not able to prove that all groups are unimodular, which is good because there are groups that are not unimodular. But if you have a lattice, the group is unimodular. Good, we have that. And now we want to define a measure on X. And I hinted already at how the claim is related to that. Yeah. We now define mx, which is a measure on our quotient x, by mx of b. B is now a subset of x, measurable subset of x. Mx of b is equal to m of, I'm only using the guys in the fundamental domain with the property that their cosets are in B. I didn't say so, but it's probably not a big surprise. The map from G to G mod gamma, or gamma divides G, the canonical map, is a continuous map, which in particular means it's a measurable map, which means that taking pre-images of measurable sets gives you measurable sets. So that's a measurable set here if B is measurable, because of continuity of the projection map. I don't want to get lost in too many of these measure theory things, so I mentioned it, but I will keep going. Okay, now I want to show that this new measure, defined like so, is invariant under translation on the right. Right? So maybe this is also something that I should have mentioned at some point. I'm mentioning it now. If you have this quotient G mod gamma and the gamma is on the left, there is no, in general, there is no map that you have on the left that you can multiply by, because the gamma is in the way. And multiplying a coset by something on the left, where gamma is on the left, might change the subgroup that is used on the left. Unless something very special happens, namely you multiply by something that normalizes gamma. Sometimes this is possible and interesting, but in general you can't multiply on the left. Multiplying on the right is perfectly fine. You did it in algebra, you can also do it here with topological things. Still well defined, even if the topology is around. But multiplying on the left is usually not okay. Okay, so this is my definition. The outcome is less or equal than the measure of the fundamental domain, right? Because I only look at the subset of the fundamental domain. So I get definitely something finite. It's a measure, all right. There's a bijective map between X and the fundamental domain, and I'm just using this bijection between the fundamental domain and X to push the restriction of the measure on H measure on G restricted to F I push this on X. This is what the formula is doing. If I take a bimeasurable map and I push a measure under a bimeasurable map one way or the other, I get a measure. That's not a big surprise. So this defines a measure on X now. And you should think of that this is now kind of the folded up space, right? This F could be our triangle, our hyperbolic triangle that with unit tangent bundle and so on. And the X is the glued up space. That's a nicer space because it's wrapped around instead of cut open. Okay, so we want to show that it's G invariant. Let G0 be in G. Then the measure of X of B, G0, I just multiply my measurable set on the right by G0, is by definition the measure of all G in F, such that gamma G0 is in B. No, it's in gamma G is in B G0. But as I already indicated, I can take this and put it instead here, but it becomes a G node inverse. Who cares? I get the measure of G in F, gamma G0 inverse is in B. And I can also do something else. I can multiply here measures. The measure I know now know the H measure on G is invariant under multiplication on the right. I now know that. So I can multiply by G node inverse if I want to, and I want to. I think the inverse is what I want to. Or not inverse, plus minus 1. Measure of G, I get now all the G. So you could call this maybe H, and I want to rewrite this using H. That's what this is about, right? I want to rewrite everything using H. Where I now talk about gamma H is in B. And then I need to relate this G to the H, but the G that appears here now is, of course, the G that appears here is H times G node. That's why maybe it's plus 1. But if the H times G node is an F, then the H is an F G node inverse again. So it's the measure of the set H in F G node inverse, gamma H is in B. I'm claiming after this substitution / multiplication on the right by G node. The set here, the measure of the set here is the measure of the set here, where I use that the measure is invariant under translation on the right. So right invariance of M is used here, which we know by the previous discussion up there. Yeah, so this was the definition. Initially, I just put this down here, so that was that step here. And now I do a substitution where instead of G's, I want to talk about the H. And the substitution is that G0 inverse is H, or G is H G0. And if the G is an F, then the H is an F G naught inverse. I'm also a bit confused about this inverse here. No, it's probably inverse. Probably multiplied by G0 inverse. Yeah. Because if your G is an H G0 and you multiply by G0 inverse, you get an H, and the H is then an F G naught inverse. Makes sense. Because the H is G, yeah. So now I think this step makes sense. I multiply on the right, this set on the right without changing the H measure by G naught inverse. Think about what happens in my substitution with H and G, and I get this expression. But that looks like my definition up here, except that I used here a different fundamental domain. Right here I have a different fundamental domain. But that's what the game is about. I have here a set that is a subset of a fundamental domain, or here a set that is a subset of a fundamental domain. And in the next step, I write down an expression that is again a subset of a fundamental domain, but of a different fundamental domain, namely the original fundamental domain. And that these two measures are the same is precisely the game one, the game from the left. And this is precisely my definition of the H measure on X, of the measure on X. So this is equal to, by definition, mx of B. So the game was really talking about maybe we have two fundamental domains with two subsets, one of the first fundamental domain, one of the other fundamental domain. But these two measurable subsets correspond to the same thing in the quotient, like here. This B is the same thing in the quotient. And this disjoint union corresponds to this measurable subset in the quotient. Is actually the full pre-image of the measurable subset in G. And yeah, the game with this cutting and rearranging and so on proves that the fundamental domain that is used doesn't really matter. The measure of this set and the measure of that set are the same, which then translates to saying that when we multiply on our quotient a Borel set on the right, that's a well-defined operation, and define the measure of the set like so, we don't see any difference to the measure of the set before, which is not everything we wanted to prove, but it's quite a bit of what we wanted to prove. Wanted to prove this invariance. We have proven the invariance. Still need to talk about the ergodicity. Good? Good, so let's prove the ergodicity. Let proof of G ergodicity again, we didn't talk much about group actions in general. So let me give you the definition and then prove what we are saying. Let B in X be such that the measure of the symmetric difference B, mx measure of the symmetric difference of B with BG is equal to 0 for all G in G. Then one of two things should happen. Either the set has measure 0 or the complement of the set has measure 0. That's what we want to prove. That's the claim for ergodicity. Okay, we define a set in G. So that's a set in X, and now define a set in G corresponding to the set in X by taking all possible pre-images. So these are all G's and G's for which the corresponding point in the quotient belongs to my original set B. And yeah, let's again ornament the G here by G0, because here I have another G. Yeah, so this set is gamma left invariant, right, by definition. Note BG is equal to gamma BG for all gamma and gamma. So in some sense, to understand what's going on with the set, it suffices to understand what's going on in the fundamental domain. Right? If you insert here gamma, a little gamma, you don't see it because there's a capital gamma. Okay. Or shall I do it with a function? Let G0 be in G, then M original H measure of BG symmetric difference BG G0 intersected with F is actually the same thing as the B symmetric difference BG0. Whatever happens in the fundamental domain corresponds precisely to what happens in the quotient. They're in a one-to-one relationship, the fundamental domain and the quotient. Measurably, they're in a one-to-one correspondence. Topology-wise, the fundamental domain is less nice because it's not a manifold. It has cuts, has boundaries, and so on. So when I think of X as a manifold, I should really think about X. But when I do measure theory, I can switch to the fundamental domain without any problems. And my H measure restricted to the fundamental domain really corresponds to the measure that I defined on X under this one-to-one map. And okay, I didn't write this down in glorious details, but this would be a nice exercise to think about. But this we know is equal to 0 by our assumption on the set B, right? This is, the set B is supposed to be having this invariance. And if this is true for one fundamental domain, of course it's true for all other fundamental domains as well. For all translates. And if this is true for all translates of the fundamental domain, there are only countable many of these. Maybe another question why gamma is always countable in our setting, but it is. Then I get that the measure of these sets BG and BG translated in G, the symmetric difference, the H measure is 0. As this holds for all gamma in gamma, our PSL2Z example is definitely countable. So in this example, we don't need an extra exercise. This holds for all gamma in gamma. We obtain MBG symmetric difference BG G0 is equal to 0 for all G0 in G. But such sets we discussed in the previous lemma, namely the lemma called ergodicity for G. So the measure of this set needs to be 0, or the complement needs to be 0 by a previous lemma MBG is 0, or M of G without B0 is 0, which implies Mx of the original set is 0, or Mx of X without the original set is 0, which is now the other thing we claimed, this ergodicity. Okay. That's BG. Thank you. This one. Yeah, thanks. Okay. So now we are happy with that proposition. But last week last week I made stronger claims. I claimed that the geodesic flow, or the time one map of the geodesic flow, that they are ergodic. We now have the measure, and we now notice that the transitive action is ergodic, which is kind of transitive action. Yeah, okay, but it's ergodic. To prove the ergodicity of the subgroups of the diagonal subgroup, or even an element of the diagonal subgroup, which is the time one map of the geodesic flow, or to prove ergodicity of the unipotent flows, the horocycle flow that we talked about, we need a bit more tools, right? So far, I always asked you when we were about to start an ergodicity proof, what do I use? And you always gave me the same answer, and it was always the correct answer. This time it wouldn't be the correct answer. So Fourier analysis is not going to be helpful. It depends a bit, of course, on the definition of Fourier analysis, but if you just think of Fourier series, Fourier integrals in the way you learn it in analysis 4 or functional analysis, then no, then this is not going to be helpful here, because this is not a torus. It's not a vector space, it's not a torus. This is different. It has curvature, it's more interesting. So we can't use our characters in any useful way. Instead, what we are going to use is, again, functional analysis from a slightly different part, not so different, but yeah. And for this, it's good to have a bit of language that goes with it. And that language part is maybe coming up in this proposition. We are probably not finishing today, but unitary representation. You can do it without that as well, but I think it's a nice excuse to do a bit of functional analysis. So let's go for it. Okay. Representation is sort of a phrase that is often used when you have a group acting on a vector space by linear maps. So there is a vector space. Which vector space? Unitary. So maybe it's a Euclidean vector space. Maybe it's a Hilbert space. Yes. So the vector space on which our group G is acting is the L2 space of our X. Okay. And then we want unitary operators on this L2 space, which makes it unitary, and then we want a representation, which means that composing the group elements and composing the linear maps is compatible. And there's something else which is a continuity requirement, which is not mentioned in the phrase, but is part of the definition, and all of that we are claiming here. Okay, so how do we say this? For same assumptions, let gamma be a lattice. Then G goes to pi G, and pi G is a map from L2 of X to L2 of X, which sends an F to pi GF is a unitary representation i.e., what do I want? I want pi identity is the identity, pi G1, pi G2 is pi G1, G2, and pi G is unitary. Right, it's a map from a Hilbert space to Hilbert space, so it makes sense to ask it to be invertible, norm-preserving. That's what unitary means. And I want one more thing, namely I want a continuity requirement, but that's sort of a small technical thing that we also had at some point with measures, I think, but never mind. You don't ask continuity in the operator norm. Operator norm is the wrong topology here. It's just absolutely the wrong topology, because if you would require it, you would have not 0 examples, but basically 0 examples, almost 0 examples. So you can't require continuity in the operator norm. Instead, you require it in what is called the operator topology, strong operator topology. Whatever, I'll just define you what I want. And for any L2 function, G in G is mapped to pi GF in L2 is continuous. So that's a map from our topological group to a Hilbert space, and we want this to be continuous. But of course, I haven't defined you yet what this pi G is, pi GF is, where pi GF is a new function on X, but it's the shifted function. And the right thing is here to multiply on the right by g. Yeah, we'll see that this is okay. And we can do something. Some things we can get rid of. I think we can get rid of unitary, because this is something we talked about at length at the beginning of ergodic theory, that when you have a measure-preserving transformation and you compose with the measure-preserving transformation, you get a norm-preserving map. And when the measurable map is invertible, which now it is because we have group action, then this measure-preserving thing will have the corresponding operator will have an inverse operator. So, proof, unitarity follows from the discussion of the Koopman operator. Because that's the Koopman operator for invertible maps. Okay, so that's a yes, we did it. Here there's nothing to show. If your G is the identity, you're not going to get a new function. You have a question. You have a question. This one? Yeah. No, they don't. One of us is right. We will see. We'll do a calculation. Yeah, I have lots of analytic number theories behind me. So they actually, so number theories prefer this quotient, and one reason they prefer this quotient with gamma on the left is that this formula is a bit easier, because you don't need to write the inverse here. One of us is right. We'll see. The continuity we'll do next time. So let's do this one. I'm not saying it's not confusing. It is confusing. And yeah. One needs to be careful how to open the parentheses. So let's open the parentheses. Let G1, G2 be in G, X in X, and F in L2. Then, let's say we do pi G1, pi G2, F at X, right? So this is a function that's a function like F tilde, and I use the definition of pi G1. Pi G1 looks at this function, this is my F tilde, and takes this function and evaluates it at X G1, because that's my F tilde. And now I look at the definition of pi G2. I think of this as an X tilde. That's a point where I want to evaluate this function pi G2F at X tilde. So I need to use the definition of pi G2, which says take the inner function F and evaluate it at X tilde G2. But X tilde G2 is X G1 G2. So I get pi G1 G2 F at X. So pi G1 composed with pi G2 is pi G1 G2. Just follow the definitions and we'll get to it. Yeah, so the continuity is what's left, and I'm claiming if you have the continuity, there are some cool tricks one can play with Hilbert spaces, unitary operators, and get the ergodicity of the geodesic flow rather quickly, ergodicity of the horocycle flow a bit less quickly, but we'll get it. And after that, we'd use a bit more functional analysis to prove that the geodesic flow is also mixing. And then we'll see where we are, and one can keep going and make it more general or prove more theorems. We'll see. Thank you.